Hello, my name is Kendall Lam, and this is Lab 2, Motion of a Falling Object. So the purpose of this lab was to compare the motion of a falling object using real-life observations and computational models both with and without drag. For physics principles, first one is Newton's second law, net force equals change in momentum over change in time, and this one is important for this lab because we want to see how changing the net force will affect the rate of change of momentum. And another important one is the velocity update formula, which, as well as the position update formula, which were both used in GlowScript to help model the motion of the object. And for our forces, the important ones for this lab are the force of gravity and the force of drag. Close to the Earth's surface, the force of gravity has magnitude mg and it points in the negative y direction, and the force of drag has magnitude b speed squared, where b is a proportionality constant and it points in the opposite direction of the velocity. And the summary of this lab is that the model accounting for drag better predicts real-life observations. So for the setup of the experiment, system was a crumpled paper ball, surroundings was earth and air, the initial position vector was taken from tracker, and the initial velocity is 0 because the paper ball is dropped from rest. So here's the actual video of the experiment. You can see that the axes and line up so that the origin is at the initial position of the ball, and the ball is being tracked using these red dots here. And you can see in the position versus time graph that the speed is increasing over time, but the magnitude of the acceleration is decreasing because the slope of the line is getting a little more linear over time. Now we're here in GlowScript looking at the no drag model first. You can see that this loop right here runs for 0.667 seconds because that's how long the video took. Here is the force due to gravity, which follows the equation that I discussed earlier in the video, and that net force is just simply set to this since there are no other forces. Here are the velocity update and the position update in order to model the motion. And let's go ahead and look at the actual running of the program. You can see here the position versus time shows that the speed is increasing over time, and here the velocity is changing at a constant rate. Now we're here at the drag model, pretty much the same thing, except we also have this force of drag added in here, which also follows the equation that was shown previously in the video. We add that to net force, and everything else remains the same. Looking at the program, you can see that the force of drag gradually increases as the velocity starts to, the magnitude of the velocity starts to increase, and that is what is causing the magnitude of acceleration to start decreasing, and why the velocity is starting to flatten out. So now for the comparison of the models, it's clear that the drag model models the real-life observations a lot better than the no-drag model, and the no-drag model predicts a much greater change in position, which makes sense because there isn't the drag slowing it down in that model. And you can also see that initially all three lines start pretty similar, but the no drag model starts to veer off quite a bit as time goes on. And that makes sense because in this lab, drag was modeled to be proportional to the square of the speed. So as the speed increases over time, the drag force is going to have a bigger and bigger impact on the net force. So for sources of error, the camera angle slash perspective, the low frames of the video, which causes blurring, they could all cause imprecise tracking of the ball. Now let's talk about the terminal velocity predicted by the models. So in the gravity-only model, there is no terminal velocity being predicted because velocity is changing at a constant rate. The slope stays the same throughout, so that would continue on as time goes on. But for the gravity and drag model, you can see that the slope is flattening out over time, which means the acceleration is decreasing. The magnitude of the acceleration is decreasing, and that means that eventually it's going to become 0 as the object gets fast enough, and that is when the velocity will reach terminal velocity, and F drag will equal F gravity, so the net force will equal 0. Now let's talk about if the terminal velocity would change if the object was initially thrown downward. No, it would not, because the speed at which terminal velocity occurs is only dependent on m, g, and b, none of which are changing in this scenario. According to this equation, which sets the magnitudes of the force of drag and the force of gravity to be the same. And in GlowScript, you can see that this is true when the model starts with 0 velocity and the model starts with -2 velocity. They both reach terminal velocity at around -4.4 meters per second, regardless of the initial velocity. So it would not change. Thank you for listening.